All right. So take a few more minutes to just try to finish up the Turkey data set. So, add up. Kind of at least write a paragraph. Nothing's blocked. So kind of get this finished up. Write your sentence. Make sure you include everything. What we'll do is we'll check it. We'll check yours in relation to mine. We'll also kind of step through how to do it too. team. Why? How are we doing? I'll say maybe like 5 more minutes, and then we'll review this. All right. So, what'd you get? Did turkey weights differ by brand? Yes? Which ones are different? You showed them all different. Yeah. All right. Go through this. All right. So I loaded up the car package. Loaded up. We got Butterball, Honeysuckle, Riverside. Now I could have used the QQ plot in car to have all three made, but because we had so many data points, I just went ahead and did them separate so we can actually see them a little bit more clearly. And yeah, these look to be normally distributed. This one, maybe not. I've got some slight curvature, maybe. But this one, I think, clearly normally distributed. Yeah, I got a couple points, but those are right at the end. Same thing, this one, just a couple points. These two that are outside. So 2 out of 3 is pretty good. And even this one, you know, that point is out, that point's out. Those two are out, and then these are out. You've got a large sample size, and 2 out of the 3 look to be normally distributed. 1 probably is non-normal. I think I'm gonna say it's probably okay to use. However, because the fact that this one appears to be non-normal, I'm gonna err on the side of caution and do Fligner-Collin. All right, to test for equal variance. So if I have one that looks like it's non-normal, but the others are look to be normal, I'm going to err on the side of caution and just go with Fligner-Collin. In this case, I get a p-value of 0.02, suggesting that the variances are not equal. All right, suggest that the variances are not equal. If I had a p-value of, let's say, 0.06, 0.07, then I'd start to question whether or not I have enough power with this test. But we got significant. So I'm going to say, let's go ahead and do permutational ANOVA, just because we have unequal variance and probably have a slight violation in normality. So for the permutational ANOVA, I run my script, and this is weight as a function of brand. Once it ends, I get a p-value that is pretty small. So this is the smallest value that we can get. It's just basically the f observed is the only value that equals or exceeds the f observed. It is that value. None of the randomized samples ever produced a f-rand value, an f statistic value, that equal or exceeded that. So the chance that we're going to see that f observed just by chance alone is really, really small. Something other than chance is giving that difference, and that something is possibly our brand. So just looking at our average weights, you can see Butterball is 9.89, Riverside is 12.33, Honeysuckle is 24.07. How did I get that? Those are the averages. I can use the aggregate function to get that, and I can see, yeah, it looks like these are pretty different, and I'm not surprised to get such a small p-value. I mean, look at it, 24.07 versus 9.89. That's pretty big. All right, so the next step then is to say, okay, well, which of these are different? And really, what I'm concerned with is this, these two, Butterball and Riverside. Are these two really, are they different from each other, or are they similar? Because I'm kind of suspecting that this 24.07 is larger than the rest. We'll confirm that with permutational t-test. So I copied and pasted my t-test script, all right, and I'm doing, you know, Butterball versus Riverside, Butterball versus Honeysuckle, and then Riverside versus Honeysuckle. And these are all brands that you can find over at HEB. Well, you could years past. I don't know, COVID, who knows? or you're probably getting some off brands. Like, I don't know, a lot of the brands that you're used to might not be available. Go look for hand soap, like soft soap. Oh man, like you can't find it at HEB. They got some other stuff. So, pairwise t-test, I did 10,000 replicates. All right, I'm not gonna run it because I know it'll take a little bit of time, but those are all of my p-values. We have the minimum p-value for every single comparison. And you'd be tempted to say, well, this is the minimum, so therefore they will be significant, but we can't do that. We still have to adjust for our p-value. Which p-value method to use is your choice, but basically, since they were the same p-values, we got the same p-values for both methods. All right, and both methods told us that all of our means differ. If we went ahead and did a plot of this, data equals Turkey, right? It gives us the same impression that, yeah, this value is really high, and when you look at these two, we know statistically that they are different. Butterball is the smallest, honeysuckle is the largest. Now you might ask, what if we just went ahead and did a Welch's ANOVA? Right? The normality assumption was a little bit questionable. What if we said, hey, we're going to proceed with the normality, ANOVA is robust to this, but we'll address the unequal variance. Could we do it? Yeah, you could. And this is what we'll get. So the one-way test tells us that we have a difference. That's great. All right. What about our post hoc test? Well, if we have unequal variances, we have to account for that unequal variance. Right? We have to account for that. So what we can do is to make my subsets, right? Much the same way as we did in the permutational ANOVA. And then I ran Welch's two-sample t-tests here to get all of these p-values. And then what we have to do is adjust these p-values. So take that. I'm going to copy this one. So we would do p-val is 2.2e negative 16. That, and then 2.2e negative 16. All right, yep. And then p dot adjust, p-val method, I use home, and I get same types of p-values. So we arrive at the same answer either way. I will point out there is a p.test function. It's a little bit different. So you have to give the x value, the dependent variable, and then you have to specify g, which is our grouping variable. All right. Now here's the thing. There is a p.adjust method in this pairwise t-test. So I can say method equals home. P.adjust method, should probably do this. P.adjust method is home. And then the other thing that you have to actually do is do this pool.sd equals f. So we don't want to use pooled standard deviation because we're running these pairwise tests. All right, we're running these pairwise tests. And what that pooled standard deviation does is it assumes the equal variances. So with this pool.sd equals f, it says don't assume that. Don't assume equal variance to calculate your pooled variance. Go ahead and calculate it for each comparison. And what you get when you run it is these p's values, which are these. why I don't get that. Let's see here. Why it didn't work? Something's not working right. Turkey. Sometimes it works. It worked on my previous paired is false. We should have gotten the same ones. We're not. I don't know why we're not. I don't know why we're not getting this. HBR. It run that, right? That's my 025. So, hold on. I guess it didn't run that. It didn't run that before. There's our p-values. They match up. This, I believe, is rounding. So 2.2e to the negative 16, this got smaller because of the methods. It's doing it one at a time, and it can go, it'll report the output one at a time, whereas this is not. So I think a clear example is this one that we did. So that oak tree, which used Welch's t-test. These were the p-values that we used, and this was Bonferroni adjustment. If I use pairwise.t.test here, I get the oaks, or that's our grouping variable. Diameter's x. P.adjust method is BONF for the Bonferroni. Pool.sd. We get these same p-values. Those same ones are the same ones that we have here. So you can get it. I just prefer not to use that pairwise.t.test. I like to know exactly which comparisons I have recorded. All right, questions? Did you get it? Yes? All right. Moving on. Move up to the board. So, there we go. Said we're gonna kind of wrap things up. All right. So, what we've done is ANOVA, right? So we had this situation where first thing we had to do was look at how many variables we had, right? We started the class with one variable, right? And we started with a continuous variable. So if we had one continuous variable, how do we present it? What kind of display did we use? What's that? What is a continuous variable? Give me an example. Aperture length. That works. All right. So if all you have is aperture lengths, what figure would you use?
histogram?
Alright, so you make a histogram. Shows the data. Now, what kind of tests can you run on it? A one-segment t-test. Run that. What else? What else can we do with one segment? And anyone that's typing in on YouTube, I can't read. There's no question. What's next? What else? So what do each of these tests do? What are they testing? These tests? Do they? So it's testing if like a median is equal to some value, right? Or if the value is equal to a median, right? That's what those two are doing, right? When do we use the t-test? We have what? Well, they're both overdue. Yeah, when we have our sample standard deviation test, right? When do we use our t-test? We have our population. All right, so t-test and z-test, that's our ones. All right. What other tests? Oh, one means variable. Sign. What is the sign test? Yeah, it tests our medians versus some other, choose some known value. Right? What else? Maybe we can do at least one more. Calvin? You had an answer. You had an answer. What was the last test that you said? Yep. Yep. Shapiro Wilk test. One continuous variable. Test for normality. Right? It's not our preferred method. QQ plots. QQ plots aren't really a test. It's more of an assessment. Alright. Almost kind of like a figure, but I wouldn't put QQ plots as showing our data to a reader or to an audience. That's all we can do with the one continuous variable. We also introduced one categorical variable. So what's an example of a categorical variable? What's that? Color, right? Sure, color. All right, what type of figure could we make? Figure or display? Yeah, we did. All right, we can put a pie chart on there, even though we didn't actually do it. Pie chart. Active work. What does a pie chart show? Percentages of a whole population. Really? Hotspot? For a categorical variable? There, IQR for sure color. Hold that thought, we'll get to it. Oh, what? Yeah, RPOP. Yeah, that's also going to show our frequencies, right? Kind of not necessarily like fun. There's one other thing that we can do. Frequency tables. So you might not think of that as a figure, but a table is an appropriate way to illustrate your data, to show your data. All right. Now the test we didn't do. We would have been moving to those. So we would have started today. But we didn't cover. It's things like binomial test, if it was dichotomous. We could do chi-square test or a g test, test. All right, that's one variable continuous category. Then what we did was we moved to two variable situation. All right. In our two variable situation, we introduced one categorical variable and one continuous variable. Right? So what type of figure we use? Consequence. That's at least doing it in R. You can also make your own plot, which would be plot of mean, confidence intervals, standard errors, and we can box plot full. All right. What about tests? What kind of tests can we do? Okay, so if we break down one continuous variable, if we only have two groups, two levels, we can run a t-test. What is a t-test and an ANOVA test? Do what? What's it test? Variance. Does it test variance? It uses variance to test something. What's our conclusion of an ANOVA? We have p-value less than 1. What's that? Difference of means. So use our variances to determine if the mean of our group is different. All right, so we can run an ANOVA. We can add two or more groups. What other tests? Brown, Forsyth, Colleen, what are those tests? Almost asked this back. They test for equal variance. These are our variance tests. So ANOVA tested for equality of means. Brown, Forsyth, Colleen tested equality of variance. There are other equal variance tests that we could run. These two are probably the most common, probably the best. What else do we run? What other tests? It uses one categorical and continuous. They're independent and dependent variables. So I'll just put randomization tests exist for most, if not all of these that we list up. There's ways to do it. Even the Shapiro-Wilk test. Give me one. Done its multiple comparison procedures. So those were the post hoc tests that we used for it. Right? They also compared our means, but they did pairwise comparisons. Just so you know, you can find significance with the ANOVA, but you might not find significance with 2P's redundance. Doesn't mean you messed up. It just means that our correction, our adjustment of the p-values, such that we lost power to detect that difference that actually exists. ANOVA picked it up, but we couldn't figure out where it exists. Any more? Oh yeah, at least. Ooh, first of all, what is that? Yep, that was our non-parametric version of our ANOVA that compared medians. Other ANOVA. It's simply ANOVA, but with a correction to account for unequal variances, which also applies to t-test, so Welch's test as well. And our Wilcox test was that non-parametric version. We did pairwise Crucible-Wallace test as post-hoc. When it's only 2 levels, we get the same p-values as Wilcox. All right. So this is kind of what we broke down. Now, what we would have done, since we would have moved to categorical, we would have talked about 2 categorical variables. 2 categorical variables. Normally the case where we don't have, one is an independent, one is a dependent variable, but both of these are kind of like independent variables. We're trying to describe our data. So frequency tables are going to work. We do mosaic plots, and then we've got chi-square and a g-test that can look at those associations, tests of independence. And then what we have been doing is getting to a situation where we have 2 continuous variables. And this is kind of it only takes about a day, like a regular 45-minute lecture to get through 2 continuous variables, because at that point we're looking at correlation. But we didn't do those either. What kind of stinks we lost this week, and then final exam is actually starting. Questions on this? So knowing what figures to use based on how many and classification variables is extremely important. Knowing what tests are available are extremely important. And knowing what each test is actually testing kind of gets us to our decision. What test should we use? So what are you looking for? What's your question? What are you interested in comparing? And then, what are the variables? How many, what type? All right? So, what we're going to do then is talk about the ANOVA. Because the ANOVA set up probably the most complex part of our decision tree. All right? So, we get to the spot where we know we want to do an ANOVA. And then, all right, so we know we want to do an ANOVA. What do we do from here? Okay, what assumption do we check first?
We random independent and normality?
We assume that we're random and independent.
Okay.
All right. So we're gonna check normality. What's our option? Yeah. Right. Is that a normal or it's not?
Yeah.
Okay. So if it's normally distributed, then what do we do? What is that testing? Okay, so how are we going to check normality? PQ plots, perfect. All right. Remember the assumption: normality within each group. So you have to do your subsets or use the car package to make all of the PQ plots. And then it's either normally distributed or not. All right. So what are we going to use for homoscedasticity check if we're normally distributed? We'll use Brown Forsythe in this case. On this case, what do we use? All right. So we can be normal and homoscedastic. We can be normal heteroscedastic. We can be non-normal homoscedastic, or we can be non-normal non-heteroscedastic. Non-normal heteroscedastic. All right. So normality assumption met. Brown Forsythe says homoscedasticity assumption is met. What do we do here? What do we do next? Not at the postdoc. ANOVA. Right? So then we run our ANOVA and we ask, is our p-value less than or equal to 0.05? We've got our choice. Yes or no? So if it's yes, what do we then do? What post time? All right. We run Turkey.csv. What is that going to tell us? Okay. Turkey, post time test. And the other is guns. Right? All right, so what is guns? Tells us which means differ from the control. So Tukey's is pairwise comparisons, all pairwise comparisons. Duns is telling us which means differ from control. All right, what if p-value is not less than 0.1? Then what do we do? Yep, we stop. The names do not differ. Stop there. We're done. All right. So heuristic test. What do we do in this? Good. Not my preferred method. What's easier than that? We're normally distributed, but we have unequal variances. Test to be run. Test is going to give us a p-value. What test do we run? Just add up all of the list of tests that went forth previously. Which of those applies? Normally distributed, unequal variance, run Welch's. So, we don't get a p-value less than 0.05, what do? We stop. Means do nothing. But what happens if we get a p-value less than 0.05? Then what do? What do we do now? What's our post hoc for Welch's? Welch's, pairwise Welch's t-test with p-value adjustment. Getting at, which means that right? They're normal. Heteroscedastic, we use Welch's ANOVA if we find a significant difference. We know at least one mean differs, then we proceed through our Welch's pairwise Welch's t-test with p-value adjustment to figure out which means differs. Now, if we're non-normal and homoscedastic, what do we do? Okay. You run Crystal Wallace. But what is this testing? Test the means? Test the means. Alright, so if we run Crystal Wallace, p-value that's greater than 0.05 or a p-value that's less than 0.05. If it's greater than 0.05, what do we do? Stop. Meanings are not different. We answered our question. Maybe we have to go back to what if we had a difference? What if we did find a difference? What do we do? What's our next step at that point? You know the medians differ. With pairwise Driscoll-Wallace, which is basically the Wilcoxon test, p-value, but we're going to have p-value adjustments. All right, what else can we do? What else can we do? So, we're not normal, but we're almost at acid. What else? Maybe we'll come back. Let's say that we violated all of our assumptions. Now what? Permutation. Permutational. And we get p-value that's less than or equal to 0.5. So if it's no, what do? Means they're not different. So what if they are? Now what? Has been the key. Pairwise permutational t-test with pairwise adjustments. So as we get these 0.05s, less than 0.05s, we're always doing some sort of post hoc test, which involves a pairwise test to figure out which means are different. One exception was with Dunnett's, where we're only comparing it to a control. We're not doing all pairwise, we're just doing a comparison to a control. Now, this part, we didn't answer this. What else can we do? If we're not normal, but we have equal variances. How good is ANOVA versus violations of our assumptions? Is it good? Is it sensitive? Is it robust? Against which assumption? Against a normality assumption? Robust against our violations of normality. So as long as we're not too bad, not overly non-normal. By overly non-normal, we're talking about massive. We're talking about a histogram that is L-shaped or backward. L-shaped. Alright. So in some cases we can ignore that normality assumption and go ahead and proceed with ANOVA. But if we do that, then we would have to be concerned. Sorry. robust versus normality assumption, but it's not robust. We can't do two. So if it is yes, if we take this route, we may need to go there if we get a significant. All right. This is our flow chart. How we process things. Start with the number of variables. Yeah. I know, but if I have something you can, you must not check that. All right. When we do the stats, we look at how many variables we have based on our question. We look at the type of variable, and that kind of specifies the test. And then once we know what kind of test we want to do, we have to go through this process of checking the assumptions. That's all the stats is just kind of going through this checklist and going down each route based on our conclusions at each step. All right? So, I didn't let someone take a picture, or probably snapped it quickly. Believe it, my writing's not perfect. On Blackboard. Here's your categorical variables. You can take a look at them. If you think you're going to be doing categorical data analysis, you can download stuff and kind of work through it. I think the presentations are pretty straightforward. But what I have is the interlude. It's a summary of the tests and flowcharts for choosing these tests. That's basically what we did. So what we just covered was this, our ANOVA. We went down and said, do we have normality within groups using a QQ plot, yes or no? And kind of based on our next step then, is it homoscedastic using the different types of test, right? And we did get to this spot where, okay, we're not normal, we're homoscedastic. All right, and then I say we can use ANOVA or a permutational ANOVA depending on the violations of normality. In some cases, you might just say, you know what, I don't want to deal with trying to explain to reviewers that ANOVA is robust. I'm just going to go ahead and do my permutational ANOVA. That works. And if you do it, then basically whatever you find out, and that's why I kind of didn't do. I did separate arrows up here, but I didn't do here. Even if you use ANOVA, if you get a significant difference, you're basically stuck with pairwise permutational ANOVA with p-value adjustments. Now, I did say Tukey's HSD or Dunnett's because if you're only slightly non-normal, Tukey's might be able to handle it. But any sort of moderate non-normality, I would not trust Tukey's. I would go ahead and run your permutational test. So everything is up here. That's what we just diagrammed to kind of step you through. This is kind of the thought process when you want to do an ANOVA. What about that first part? Here's our test diagram, our test flow. We start with variables, one variable.